Alright, so what we have here is our brick sitting on the table, and right now it's just sitting there. And Nick, go ahead and give us a gentle force to the right. Alright, so we can see there that Nick is pulling to the right, but it's still not moving. So what does that tell us, Nick?
That it's in equilibrium.
Alright, and if Nick is pulling to the right, there must be a force to the left. And what is that force to the left called, Nick?
Friction.
Friction, and in fact, since it's not moving, it's called static friction. So what we're going to do for this problem is figure out the coefficient of static friction between the brick and the table. And the first thing we need for that is to find the maximum force we can apply before the brick moves. So Nick, slowly add force till the brick moves and tell us what that force is. So what did it take to move it, Nick?
It's about 7.2.
About 7.2 newtons. Thank you, Nick. Alright guys, so for this problem we're dealing with a force called static friction, and friction is a force that resists objects sliding past one another. We call it static friction when something's trying to make them slide but they're not actually sliding. And so what you'll notice there is that static friction can be anywhere between 0 and some maximum value. So like when Nick was not pulling at all to the right, there was 0 static friction pulling back to the left. When Nick was pulling with a force of 1 Newton to the right, there would have had to been a force of static friction of 1 Newton to the left to keep it from moving. And so Nick kept pulling harder and harder, and the force of static friction kept getting greater and greater. But we noticed that when Nick pulled up to a force of about 7.1, 7.2 newtons, the force of static friction couldn't keep up anymore, and then it moved. So basically what we figured out here is that maximum tension that Nick applied has to equal the maximum force of static friction, and that value was 7.1 newtons or 7.2 newtons. I don't even remember what he said. Close enough. Okay, and of course we also know that since it's in equilibrium, N has to equal mg. And for that value, we're going to have 15 newtons. Okay, so let's define a couple things real quick, and then we're going to come back and finish this problem, which we said earlier was to solve for the coefficient of static friction. Alright, so as we said a minute ago, static friction is the force that keeps surfaces from sliding past one another, and the force of static friction can be anywhere from 0 to some maximum possible value. And the way we calculate the maximum possible value is that it's always equal to mu s times n. Okay? So this mu s stands for the coefficient of static friction, and what that actually is that tells us basically how slick the surfaces are, how easily those two types of surfaces can slide past one another. And if you see a coefficient of static friction less than about 0.1, that would be a really low value. So if you think of like a sled on ice, that might be something around 0.1 or less. And if you see something up near a value of 1, that would be like a very high value, and that would be like maybe like good car tires on dry concrete or asphalt. Okay? And then of course the other important value there is the normal force. And the normal force, remember, basically tells us how hard two surfaces are pressed together. So basically then the maximum force of static friction depends A, on the types of surfaces you're pushing together, and B, how hard they're pressed together. So if we have rough surfaces pressed together very hard, we're going to have a very high value of a maximum force of static friction. But if we have very slick surfaces and they're not pressed together very hard, then we're going to have a very low value for our maximum force of static friction. So if we rearrange that equation, we'll see very quickly that mu s is going to equal Fs max divided by the normal force. And if you go back to the last slide, you'll remember that we figured out that for this brick, the maximum force of static friction came out to be about 7.1 or 7.2 newtons. And the normal force was equal to the weight of the brick, which we've calculated several times, and that was 15 newtons. And so we have 7.1 newtons divided by 15 newtons. And you'll notice that the newtons cancel out. And so because coefficient of static friction is a ratio of two forces, the value actually won't have any units. And if we calculate that value, we get 7.1 divided by 15, which would be a little less than 1/2. Let me calculate the exact value. And we come up with a coefficient of static friction of 0.47, which is about what I would expect for a brick on a table. It's not a real low value like a sled on ice, and it's not a super high value like a car tire on concrete. It's somewhere in between, so that value makes sense.